Question 2, we're dealing with simple harmonic motion, SHM. Brad is working on a scaffold. He ties his bag to a hook, H1, which is shown there in the diagram, and using a light rope of length 5.50 meters, as shown in the diagram. He pulls the bag 0.900 meters to the side and lets it swing. So that's, before we even get into anything, that 0.900 meters would tell us that the total amplitude, that's the distance from the equilibrium position, that gives us the amplitude of swing. So A, show that the time period of the bag swing is 4.70 seconds. Again, this is a show question, so it's likely that this 4.70 seconds will be used later on. But how we do this, we've got the formula for pendulum, 2 pi square root L over G. We have L, we don't have G, but we can, if it's given in the resource, but if it's never given, we can always assume it's 9.81 meters per second squared, or newtons per kilogram. So we plug those numbers in, and our unrounded value we get will be 4.7046 units of seconds. Okay, B, calculate the maximum velocity of the swinging bag. Maximum velocity of the swinging bag. This, we have to go to the slightly trickier versions of the formula, the one that include the trig functions. But in this case we don't need to worry about the trig function bit, because maximum velocity means that our Vmax is just going to be equal to A omega, which is nice. We then have to find what omega is, but that also isn't too tricky, since we are told up above, we'll be told we just calculated it. We found the time period of the swing, because remember we're using things that come down from above there. Omega equals 2 pi f. We don't know the frequency, but we know the period, and that means frequency is 1 over the period, so omega is 2 pi over t. So we now have omega, and the amplitude of swing was 0.900 meters, which means we can just plug those numbers in, and out comes, just to be very clear, that's the time period that we use in this, and the numbers that come out gives you 1.20 meters per second, which is very, very nice. Now, just as a side note, remember the velocity at any time is A omega cos omega t. This cos omega t section, and same with the sin omega t sections, and they are a modifier. They change this maximum value. So it always starts with the maximum value and then modifies according to a proportion based on the time. So you can always remember these formulas when you're dealing with a maximum. You can just ignore that part of it. Okay, 2. Show on the diagram above where this maximum velocity occurs. Okay, scrolling back up. Maximum velocity, remember the acceleration is proportional to the displacement. So when your acceleration is maximum, that's when it's changing direction, and the change of direction is when the velocity is 0. So when your acceleration equals 0, that's when it has achieved its maximum velocity, and that point is right in the center. So that's when Vmax will occur. Okay, so cruising down again. C, explain how the tension on the rope varies as the bag swings. How the tension on the rope varies as the bag swings. Okay. This is a very, very tricky question. There is a lot of detail here. So probably the best way forward would be to explore the tension in the rope at each of the probably 3 main points. So here's our rope. We've got it at equilibrium position. we've got it at one extreme and we've got it at another extreme. So we can draw the forces on them at each point. So equilibrium position is easy-ish because we've just got the force due to gravity, and we've got the tension force, which is providing, because this is essentially circular motion, it's a slight curved path. We make a small angle approximation and assume it's travelling side to side in a straight line for the sake of our pendulum formula, but it is, this Ft is really the centripetal force at every single point along here. And at this point, the velocity is max, as we saw earlier. So maximum velocity means you'll have maximum centripetal force, because it's mv squared over r. And if it can't provide that force, the rope will just break. But we know it does provide that force. So if we're explaining how the tension on the rope varies as the bag swings, we'd say the tension is probably going to be maximum in the centre, because that's when the centripetal force is maximum. So Ft max at equilibrium, since Fc is max, and at either end, I'm going to have to draw this in a slightly different colour again. We've still got the force due to gravity, but a proportion of that force due to gravity is being used to bring bring it back to equilibrium, and the tension force is just kind of dealing with that vertical component of gravity. Now I've drawn something just a little bit off here. This here should be on a slight downward angle, because it's a component of that gravity force. If we just zoom in and have a little look, there's going to be your force due to gravity directly down, because it's on a slight upward, slightly raised from where the equilibrium position was. That force, that component of force due to gravity, which is restoring force, bringing it back down, will be there. And then we've got the tension force, which, if you shifted the tension force down to here, would complete the triangle. Which is opposing just that component of the gravitational force. Now, anyway, the main point is we've seen that the centripetal force will be 0 right at the extremes, which means that the tension on the rope must be minimum at those points. It'll be just enough to balance the vertical component of force due to gravity, but whereas in the centre it's dealing with the entire vertical component of the force due to gravity, the tension force is on an angle now, and it's only dealing with that portion, not the entire vertical portion. Part of that vertical portion is applied at an angle to be the restoring force. Okay, so I think that's relatively clear. Moving on. D. Explain how the maximum velocity of the bag would change if Brad had used a longer rope to attach his bag to the hook H2, and we're assuming that the bag is given the same initial displacement. So L is increasing, and we want to know how Vmax changes. Okay, so probably the best way forward is to look at, because we followed the process through with some calculations, we could just look at our equations that we used to do that and follow the mathematical patterns to see what will change. So we can see that L is increased, so T will also increase. That's the time period. That means since omega equals 2 pi over T from earlier, remember 2 pi f, 1 over f is 2 pi T. Since T is increasing, the angular omega is decreasing. That means that our Vmax, which was A, same amplitude, A omega, that means since omega has decreased, that means Vmax has decreased. Okay, following through. You can rewind the video and watch it again. I won't repeat myself. Okay, this one looks like a goodie. Brad offers his friend Anne a sandwich from his bag. He lets the bag swing when Anne is 1.4 meters away. He calls to her when the bag has travelled 0.100 meters. Anne's reaction time is 0.400 seconds. Calculate the time between Brad's call and when the bag reaches Anne. There's a little bit of... Okay, we've got a diagram. Let's see if that helps us interpret what's going on. I see. So it's starting from here, which if we're on our diagram, we could represent at this point. We'll call that 1 and 1, just so we know. It's Anne's... Where are we? She's 1.4 meters away, which isn't quite to the extreme end. So remember, phasors move anti-clockwise. So we follow it all the way down and around till it reaches 1.4 meters, which isn't quite all the way to the end. So that's position 2. And I'll tell you what's confusing me. It says Anne's reaction time is 0.400 seconds. I'm assuming, I think we can assume that means she's ready to catch it at 0.400 seconds. So I'm not sure if that's a relevant data, to be honest, but we need to find the time between Brad's call. So he calls her when the bag has travelled 0.100 meters, which is actually about here, which would mean that distance here is 0.8, which means this distance here, up until the 2, being 1.4 minus 0.9 is 0.5 meters. Okay, so we're trying to calculate the time between Brad's call and when the bag reaches Anne. So I guess we're looking for the time to travel from this position here, which we'll call position 3 just for convenience. So position 3 to position 2. So time for position 3 to 2. Okay, let's have a look at it then. So the best approach, I think, is to work out, because remember we know the angular frequency, and this is from H1, so we can stick with our original time period and our original angular frequency. I think the best thing is to work out this angle, because the angular frequency is the angle covered over time, and just rearrange the equation to find what the time equals. So remember, time will equal theta divided by omega. Okay, so theta we can work out using our triangles. And since the video is getting on a little bit long, I'm not going to calculate that in detail, but we do know this length, 0.8 meters, and we know the length of the pendulum is 0.90 meters. So we can work out the angle and take it away from the 90 degrees here. Then we can do the same from this side. We know 0.5, and we know that 0.9. We can work that angle out and take it away from this 90 degrees. So once we have that angle, which, let's see if the answer is provided. No, it doesn't. Oh, yes, it does. It works out to be 1.68 radians. So theta equals 1.68 radians. And the angular velocity from above, remember, was... I'll just cruise up and have a look. Angular velocity was, I don't think we actually calculated it, but it's 2 pi over the time period, which is 4.7 seconds. So if we go all the way back down, 2 pi over 4.7 seconds, substitute those numbers in, press equals, and you should get 1.26 seconds. There you go. Quite convoluted, but you're basically just finding the angle from the information given and using the angular frequency above, and it's actually a very simple equation, but it's just complex trying to interpret the question, so you're getting marks for interpreting. Okay, really important to read lots of questions, get exposure to lots of questions so you can interpret them better.